Hello, good morning. Okay, this lecture provide a comprehensive introduction regarding the underground cables, which are an essential component of modern power transmission and distribution systems, and especially in urban and environmentally area. And I will begin with a general overview of underground cables and their importance, and then followed by a detailed explanation of their construction, including the various layers and components that ensure safe and efficient operation. Uh, the lecture then explores different types of insulating materials and their roles in maintaining electrical integrity under various operating conditions. Next, I will examine the classification of cables based on voltage levels, constructions, and applications, and both single core and multi-core cable design will be discussed here to highlight their advantages, limitations, and typical use cases. And at the end, eventually, the lecture introduced the concept of superconductors, providing insight into advanced technologies that have potential to significantly enhance the performance and efficiency of future power systems. Okay. Okay, this slide outlines the main topics that will be covered throughout the lecture on underground cables. I will start with an introduction to understand the role and significance of underground cables in power systems. Then I will examine the construction of cables, focusing on their structure, components and how each part contributes to reliable operation. The lecture will also discuss different insulating materials which are critical for ensuring electrical safety and performance. Following this, I will look at the classification of cable based on various criteria such as voltage levels and design features. In addition, both single core and multiple core cables will be studied to compare their characteristics and applications. And finally, the lecture will conclude with an overview of superconductors, introducing advanced technologies that may shape the future of electrical power transmission. Okay, this slide present the more advanced analytical topics that will be covered in this lecture on underground cables. I will begin by examining the insulation resistance of a single core cable, which is crucial for understanding leakage currents and overall cable performance. Next, we will study the capacitance of a single core cable and how it affects charging currents and voltage behavior. The concept of dielectric stress is then introduced to analyze how electric fields are distributed within the cable insulation. And we will also explore the most economical conductor size, balancing efficiency, cost, and thermal limits. In addition, the lecture covers cable grading techniques, which are used to improve the distribution of electric stress and enhance insulation life. The, the effective resistance of cables is discussed to account for practical losses under operating conditions. Finally, we extend analysis to the capacitance of a three-core built cable, highlighting the complexities involved in multi-core cable systems. This is very long content. Hopefully, everything can be covered in this lecture. So this slide also highlights the thermal and operational aspects of underground cables, which are critical for ensuring safe and reliable performance. The lecture will first um, introduce the concept of thermal resistance and explaining how heat flows through the different layers of the cable. Then we will focus especially on the thermal resistance of the dielectric in a single core cable, as insulation plays a major role in heat dissipation. And the discussion will continue with thermal characteristics and current rating, showing how temperature limits directly influence the amount of current the cable can carry. And in addition, the concept of permissible current loading will be explained, emphasizing the importance of avoiding overheating and insulation damage. Finally, the lecture will cover different types of cable faults, helping students understand how common failure mechanisms and practical challenges associated with underground cable operation and maintenance can be taken into account. This is very long lecture, so hopefully I will finish up to next week. This slide introduced the fundamental concept of power transmission methods, highlighting that electrical energy can be delivered either through overhead lines or underground cables, depending on some conditions. While overhead systems are widely used due to their lower initial cost, underground cables offer several important advantages, especially in urban and critical environments. And they are less susceptible to damage from external factors such as storms, wind, or lightning, which significantly improve system reliability. So, in addition, underground cable generally require lower maintenance over time and have fewer chances of fault caused by environmental conditions because of course, this is obvious because a cable is digging in the ground. So these benefits make them an attractive option for modern power system where reliability, safety, and aesthetics are key characteristics to be considered for our design. Okay, this slide continues the comparison between underground cable and overhead transmission systems by highlighting additional advantages and key limitations. Underground cables offer a smaller voltage drop due to their lower um, inductive reactance, which can improve voltage regulation along the line. They also provide a much better general appearance, making them especially suitable for urban areas where visual impact is an important consideration. However, these benefits come with notable drawbacks. The installation cost of underground cable is significantly higher due to um, installations and protective requirements. So, moreover, at high voltages, insulation becomes a major challenge as underground cables must withstand strong electric stress, making their design and operation more complex compared to equivalent overhead systems. So, depending on where is the applications, we can use one of these two options. Okay, this slide explain the situation in which underground cable become the preferred or necessary choice over overhead transmission line. In many cases, underground cables are used when it is impractical or even possible to install overhead lines. So we have to find a compromise between these two. So depending on the cost and the locations. So this slide explains the traditional and modern use of underground cables. Traditionally, they have been used mainly for power distribution in crowded urban areas at low or medium voltages. However, with recent advantages um, in design and manufacturing, underground cables can now be used efficiently at high voltages, expanding their role in power transmission systems. Okay, this slide also highlight an important development in power system due to recent improvements in cable technology. Underground cables are now capable of transmitting, transmitting electrical power, not just distributing it. So, however, their use in transmission is typically limited to short or moderate distance because of high cost and technical limitations. Okay, this slide describes the basic structure and selection principle of underground cables. And underground cable mainly consists of one or more conductors that are insulated with suitable materials and protected by an outer covering to ensure mechanical and environmental safety. So, although different types of cables exist, the selection of the appropriate type depends on the operating voltage and specific service requirements of the power systems. Okay, this slide outlines the essential requirements for a good underground cable design. First, the conductor material should be either standard copper or aluminum with high electrical conductivity to ensure different power transmission. Stranding of the conductor is important because it increases flexibility, making the cable easier to install and handle. So it also helps improve current carrying capability by allowing better thermal and mechanical performance. Okay, this slide highlights two key design requirements for underground cables. First, the conductor size must be properly selected so that the cable can carry the required load current without overheating, while also keeping the voltage drop within acceptable limits. So second, the insulation must have sufficient thickness to ensure a high level of safety and reliable operation at the specific operating voltage. In this slide, I want to emphasize the mechanical and material quality requirements of underground cables. The cable must have adequate mechanical protection to withstand the stresses and rough handling during installation and laying. In addition, all materials used in cable construction should have strong chemical and physical stability to ensure long-term performance without degradation. So here for cable, also similar to battery, we have a degradation. So after a long time, the efficiency of the cable can be reduced. So this helps maintain reliability and extends the service life of the cable under various operating conditions. Okay, this slide introduces the construction of underground cables, especially focusing on the general structure of a three-conductor cable. The accompanying figures illustrate how such a cable is built with multiple layers, each serving a specific function such as current conduction, electrical installation, and mechanical protection. So, for example, some of this cable should be able to use in a very stressful environment, for example, in particular company or in the oil companies. So they have to have some special ability. For example, we need to, the cable should have armor in order to save from the mechanical protection and so on. So this overview helps you understand the layer design approach used in cable engineering to ensure safe and reliable operation in the power systems. Okay, this slide lists the main part of an underground cable. The conductor carries current while insulation prevents electrical leakage. Uh, Metallic shields protects against moisture. Bedding uh, provides cushioning, and armoring gives mechanical strength. So finally, serving acts as the outer protective layer against environmental effects. For example, in petrochemical company, this it can help to protect cable against the very dangerous material. So this slide explains the cores or conductors in underground cables. A cable may contain one or more conductors depending on its application. For example, a three-conductor cable is used for three-phase systems. The conductors are typically made of tinned copper or aluminum and are standard to improve flexibility and reduce the skin effect, ensuring better performance in AC operation. Okay, this slide explains the installation in underground cables. Each conductor is covered with a suitable layer of insulation to prevent electrical leakage. So the thickness of this insulation depends on the operating voltage, as higher voltages require thicker insulation to ensure safe and reliable performance. Okay, this slide describes the metallic schist in underground cables. A layer of lead or aluminum is placed over the insulation to protect the cable from moisture, gases, and harmful chemicals such as acids or alcohols present in soil or the surrounding environment. So this she's ensures long-term durability and reliable operation of the cable. Okay, this slide explains the beading layer in underground cables. Beading is applied over the metallic sheath and is made of fibrous materials such as um, hessian tape. Its main function is to protect the metallic sheath from corrosion and to prevent mechanical damage caused by the armoring layer. Especially in Saudi Arabia, uh, the, we have a high humidity and very hot environment, so corrosion will be happen suddenly. Okay, this slide describes the armoring layer in underground cables. Armoring consists of one or two layers of galvanized steel, wire, or steel tape placed over the beading. Its main function is to protect the cable from mechanical damage during installation and handling. In some cases, armoring may be omitted depending on the cable type and applications. All right. This slide explains the serving layer in the underground cables. Serving is the outermost layer made of fibrous material such as jute applied over the armoring. So its main purpose is to protect the armoring from atmospheric conditions like moisture and corrosion, so ensuring long-term durability of the cable. Okay, this slide I wanted to introduce the importance of insulating materials in underground cables. The reliable operation of a cable largely depending on the quality of its insulation. So therefore, the insulating material must have high duality strength to prevent electric breakdown under high voltage conditions. It should also possess high insulation resistance to minimize leakage currents and ensure efficient and safe performance of the cable system. Okay, this slide continues the required properties of insulating material used in underground cables. The insulation should have high mechanical strength to withstand handling and installation stress. It must be chemically stable and resistant to acids and alcohols over a wide temperature range. So in addition, it should be easy to manufacture and process, cost effective and non inflammable to ensure safety in operation. Especially should be very non-inflammable in very flammable environment like companies, oil industries. So this slide explains another important properties of insulating materials. They must be non-hygroscopic, meaning they should not absorb moisture from air or soil. So moisture significantly reduce insulation resistance and accelerate the breakdown of the cable. Therefore, if an insulating material is hygroscopic, it must be properly protected with waterproof covering such as lead sheets to maintain reliable performance. Okay, this slide concludes the discussion on insulating materials by emphasizing that no signal material possesses all the required ideal properties. So therefore, the selection of insulation depends on the intended application of the cable and the level of insulation performance required. So engineers choose the most suitable material by balancing electrical, mechanical, thermal, and economic considerations. Okay, this slide lists the main insulating materials used in underground cables. Common materials include rubber and vulcanized India rubber, which provide good flexibility and insulation. Uh, impre- Impregnated paper and varnish cambric are also widely used in traditional cable designs. And in modern application, synthetic materials such as uh, polyvinyl chloride or PVC and cross-link um, polyethylene or XLPE are preferred due to their superior electrical, thermal, and mechanical properties. So, based on my previous experience in industry, these two materials are usually used in, especially in industries. So this slide describes rubber as an insulating material used in cables. Rubber has reasonably good insulating properties with relative permittivity between 2 and 3. Uh, Dielectric strength of about 30 kilovolt per millimeter and a high resistivity of approximately 10 over 17 ohm centimeter. So, however, it has two major drawbacks. It really absorbs moistures and its maximum safe operating temperature is low, around 38 degrees centigrade, which limits its use in high temperature applications. So this slide highlights the limitation of pure rubber as an insulating materials. So it is soft and easily damaged during rough handling, and it also deteriorates or ages when exposed to light. So because of these weaknesses, pure rubber is not suitable for direct use as cable installations. Okay, this slide explain vulcanized India rubber (VIR) as an improved form of rubber installations. And VIR is produced by mixing pure rubber with mineral materials and then undergoing a process called vulcanization, which enhances its properties. As a result, VIR has a higher mechanical strength compared to pure rubber. However, its main disadvantages is that the sulfur used in the vulcanization process can react with copper conductors, which may affect the long-term performance of the cable. Okay, this slide explain an important practical aspects of vulcanized India rubber VIR insulation. Since sulfur in VIR can react with copper, thin copper conductors are used to prevent this chemical reaction. So due to its limitations, VIR insulation is mainly applied in low and medium voltage cables rather than high voltage systems. So this slide introduces impregnated paper as an insulating materials. So it has largely replaced rubber insulation in many applications due to its better performance and reliability. So its main advantages include low cost, low capacitance, high dielectric strength, and high insulating resistance, making it a widely used option in underground cable systems. So this slide highlight the main limitation of impregnated paper insulation. So although it offers several advantages, its key drawback is that it is hygroscopic and tends to absorb moisture. So even after integration with suitable components, moisture ingress can still occur, which reduce the insulation resistance of the cable. Therefore, paper insulated cables must always be properly sealed and provided with protective covering to prevent moisture penetration and ensure reliable operation. Okay, this slide explains the practical precaution for impregnated paper insulated cables during the installation. If the cable is left unused on site during the laying process, it's exposed and must be temporarily sealed with wax or tar. This is very important, especially in industry. So this prevents moisture from entering the insulation and helps maintain the cable insulation quality until final installations. Okay, this slide introduces varnish cambric as an insulating material. It consists of a cotton cloth that is impregnated and coated with varnish and is also known as empire tape. So since varnish cambric is hygroscopic, cables using this installation must always be protected with metallic sheets to prevent moisture ingress. So its dielectric strength is around 4 kilovolt per millimeter, and its relative permittivity ranges from 2.25 to 3.8. So this slide describes PVC as a synthetic insulating material used in cables. This is very common in industry. It is typically available in the form of a white powder and is widely used due to its excellent properties. PVC offers high insulation resistance, good dielectric strength, and strong mechanical toughness, maintaining its performance over a wide range of temperature. So this slide highlight the advantages and limitation of PVC installation. PVC is chemically stable and resistant to oxygen, alkalis, and many acids, making it suitable for harsh environments such as cement and chemical factories. So, however, its mechanical properties such as electricity are um, poorer compared to rubber. So, therefore, PVC insulated cables are mainly used in low and medium voltage domestic lighting and power installations. So this slide introduces XLPE as a modern thermostat insulations material used in cables. So XLPE is produced by a process called cross-linking, in which the molecular structure of polyethylene chains is modified so that they become more tightly bonded together. So this process improves the material's thermal and mechanical properties. Uh, Cross-linking can be achieved through either chemical or physical methods. Okay, this slide explains the advantage of polythene polyethylene and how cross-linking improves its performance. PE has excellent dielectric strength, high insulation resistance, and low dissipation factor over a wide range of frequencies, making it a very good insulating material. However, its main limitation is its relatively narrow operating temperature range. By cross-linking PE to form XLPE, the temperature imply capability is significantly improved while maintaining its excellent electrical properties. So this slide introduces the classification of underground cables. Cables used for underground service can be categorized in two main ways. First, based on the type of insulating materials used in their constructions, and second, according to the voltage level for which they are designed and manufactured. So this slide presents the classification of underground cables based on voltage levels, which is the most commonly used method. Low tension cable are designed for voltages up to 1000 volt, while high tension cables operate up to 11 kV. So super tension cables cover the range from 22 to 33 kilovolt, and extra high tension cables are used for voltages between 33 kilovolt and 66 kilovolt. And extra super voltage cables are designed for systems above 132 kilovolt. This classification helps in selecting the appropriate cable type for different power system applications. Okay, this slide explains that underground ground cables can be designed with different numbers of cores depending on the service requirement. A cable may be single core, two core, three core, or four core, and so on. So the number of cores can be selected based on the type of the electrical system and the nature of the load being supplied. Okay, this slide explains cable selection for three-phase systems. So for a three-phase service, either three separate single core cables or one three-core cable can be used. So the choice depends mainly on the operating voltage and the load demand. Each option also has its own advantages in terms of installations, cost, and the performance. Okay, this slide describes single core cables used mainly for voltages up to 6.6 kilovolt. At this voltage levels, the electric stress are relatively low, so no special design measures are required for field control or thermal performance. The cable consists of a single circular conductor surrounded by concentric layers of installations and protective materials. So this slide is showing the cross-sectional structure of a paper insulated power cable. At the center, a standard copper conductor is used to efficiently carry current while maintaining flexibility. Surrounding it is impregnated power insulation, which enhances the electric strength and prevent moisture ingress. So a lead shells encloses the installation, providing a protective barrier against mechanical damage and environmental factors. So finally, the outer serving layer adds extra mechanical protections, and in overall this layered design ensure reliable electrical performance and long-term durability of the cable. Okay, this slide explains additional characteristics of a single core cables. They are generally not armored to avoid excessive losses in the metallic sheaths. The main advantages of single core cables are their simple construction and the ability to accommodate a large cross-sectional area of copper, which improves current carrying capability. Okay, this slide introduce multi-core cables used in practical power system. Underground cables are commonly required for three-phase power delivery, which can be achieved using either three single-core cables or a single three-core cables. So for voltages up to 66 kilovolt, three-core multi-core cables are generally preferred due to economic advantages as they reduce installation space and overall cost compared to using separate single core cables. Okay, this slide explains the limitation of three core cables at HV systems, high voltage. For voltages above 66 kilovolt, three core cables become too large in size and impractical to manufacture or install and handle the cables. So therefore, in such high voltage applications, three separate single core cables are preferred to be installed. Okay, this slide presents the main type of multi-core cables used for three-phase power system based on voltage levels. Belted cables are generally used for voltages up to 11 kilovolt for medium high voltage applications ranging from 22 kilovolt to 66 kilovolt. Screen cables are preferred due to better electric field control for voltages above 66 kilovolt. Pressure cables are used as they are designed to handle very high electrical stress and ensure reliable operation. Okay, this slide introduces belted cables, which are used mainly for voltages up to 11 kilovolt, although in special cases they may be used up to 22 kilovolt. It also refers to the construction of a typical three-core belted cable, showing how the three conductors are grouped together and insulated within a common belt insulation layers. Okay, this slide explains why belted cables are suitable only for higher voltage levels. For voltages below 22 kilovolt, the electrostatic stress in the cable insulation is mainly radial, making the belted construction adequate. So, however, at higher voltages above 22 kilovolt, tangential stress also becomes significant. So this stress act along the layers of paper insulation and can lead to insulation failure, which is why belted cables are not suitable for high voltage applications. Okay, this slide explains the limitation of the belted cable at higher voltages and the need for improved designs. Since paper insulation has a relatively low resistance along its layer, uh, tangential stress can create leakage currents through the insulations. So these leakage currents lead to local heating, which increases the risk of insulation breakdown. To avoid this problem, screen cables are used where metallic screens safely conduct leakage currents to earth, improving reliability and safety at higher voltage levels. Okay, this slide introduces screen cables which are used for medium to high voltage applications. These cables are typically used up to 33 kilovolt, although in special cases they may be applied up to 66 kilovolt. Screen cables are designed to control electric field distribution more effectively than belted cables. The two main types of screen cables are H-type cables and SL type cables, each having a different construction method for managing electrical stress and improving insulation performance. Okay, this slide introduces H-type cables as one of the main forms of screen cables. It refers to the construction of a typical three-core H-type cable where each core is individually screened to control the electric field distribution more effectively. This figure illustrates how the cable is structured to improve insulation performance and reduce electric stress in medium voltage applications. Okay, I think it's better to close my lecture here.